Hi guys, Mr. Janowski. I'm here making another video. This is from the Chapter 35 study guide. This is problem 6. And I've got some new toys to play with, so I'm excited about that. You're going to have to cut me some slack because I'm new at these things and not great at using them all. Well, one thing, I have an external microphone. You can't see it, but it's clipped to the top of my MacBook. So hopefully the audio sounds better than it has been sounding. Also, I'm using the MacBook now, so it has a better built-in camera than the Chromebook has, so hopefully this part of the video looks at least a little bit better. Still working on the background, the mise-en-scene stuff. And finally, and most importantly, and most expensively, is I have a Wacom tablet. So this is going to let me write some of the more complicated math, which is what we're going to need to do this problem that we're going to do here. So this is where you're going to have to cut me some slack. Just opened this thing, not very good at it. I played around with it for a little bit. It's going to take me a while to get good at it. So anyhow, enough talking. Let's start doing the problem. Come on, go away. Also, I'm not good at Painter Essential 7, as you'll see. But anyhow, this is one of the really tricky, intricate problems. There's a lot going on here. So let's see what we do. So we've got this complicated circuit, a lot of resistors. We need to figure out a lot of different things about this. I'm going to skip all of the step stuff here. Just know that we're looking for a lot of things. So let's see. First, let's stick with black for now. Yeah, we've got the circuit. We need to, I don't want black, I want purple. Sorry, too many toys. We need to simplify this circuit a little bit. So let's take these two guys. I don't know why my pen looked like that. And find our equivalent for these two guys. I've got two resistors in parallel. So your formula for resistors in parallel, it's going to be 1 over the first resistor, which is R2 here. So 1 over 16 ohms plus 1 over 24 ohms. All right, so clearly I'm not good at this, but I can already tell this is light years ahead of what I had been doing with the crappy stylus in the Chromebook. So anyhow, you do this, and this is going to end up being, all right, come on. I was a little better at this before. All right, Chromebook's running slow. MacBook's running slow. This is going to give you 9.6 ohms. That won't do. That's not an ohm. 9.6 ohms. All right, hopefully by the end of this video, I'm better at writing these things. So now redraw your circuit. Don't be lazy. Redraw it. Oop. So here's our battery. Come out. We have... Oop. All right, I swear I am not changing how hard I'm pressing down here. It's just being weird. So that's 8 ohms. This is that equivalent resistance we just found out. 9.6 ohms. Draw this a little bit better. 9.6 ohms. And then we had another resistor down here. What the hell's going on? All right. This resistor down here, 32 ohms. So we've got 3 resistors in series. This is easy to simplify. Boop. So the total you're going to get out of this guy, why is that happening? I'm very annoyed. I am not writing softly. Nope. The total resistance you're going to have is going to be 8 ohms plus 9.6 ohms plus 32 ohms. That, put it in the calculator or do it in your head. 49.6 ohms. So this is the equivalent resistance seen by the battery. So this is what we were looking for at the first one. Whoop. All right, not very good at this thing yet. Next, part B, we need to find the current leaving the battery. So this is pretty easy to figure out. So we know Ohm's law, V equals IR. So that's going to give us I is equal to V over R. The V you're going to use here. Okay, this is freezing up. The V you're going to use here is the voltage of the battery, 12 volts. And the R is that R equivalent we just figured out. The 49.6. Or there's a huge amount of lag here for some reason. 49.6. I have a lot of respect for what Mr. Khan does when he's making these videos for Khan Academy. Anyhow, you do this, and the number you end up with is 0.2419 amps. So that's the current leaving the battery. In part C, we need to figure out what's the power used by this whole thing. So our formula for power is Watt's law, PIV, P equals IV. So your current is that current we just found, 2419 amps. And the voltage is the voltage of the battery, 12 volts. So plug those numbers into the calculator, and it's going to turn out that the power used by this whole thing is 2.903 watts. So there's our answer for part C. Again, still getting the hang of this Wacom tablet. All right, so this was our answer for C. This was our answer for B. Sorry, that's a letter B. And up here, this is our answer for A. All right. Now for the fun stuff. For part D, E, and F, we've got to figure out the voltage drop across each resistor, the current going through each resistor, and the power used by each resistor. So for that, didn't mean to do that. Again, I promise I'll get better at this. Come on, don't be so laggy. So for that, it's this idea up here. If you can get any one of these blocks in a row filled out, then you can just use PIV and VIR to calculate the other ones. So let's see. Right away, let me change to a fun color. It's fun. All right, blue. That's a fun color. Right away, we know that the current going through R1 has got to be this current right here. 0.2419 amps. 19 amps. All right. Because the current leaving the battery goes out here. So all of it goes through R1, comes here and splits. So I don't know the current through either one of these guys. But I do know that when it comes back together and goes through R4, it'll be that same current again. So I do know the current through R4. 0.2419 amps. Come on, that's a 9. All right. So how do I figure out the current going through here? The easiest way to do that is to come back to this middle drawing right here and use Ohm's law and figure out the voltage across this equivalent resistance. Because remember, this equivalent resistance here actually represents these two guys right here. So we'll use Ohm's law right here. Sorry, I'm still trying to use this kind of like a mouse, and the rules for using it work a little differently. So the voltage across REQ is going to be that big I times REQ. All right, so that's going to be equal to 0.2419 amps times REQ is 9.6 ohms. So if you do that, V of REQ, meaning the equivalent resistance of R2 and R3 in parallel, where have I got that number? Ends up being 2.323 volts. So where does that number go? Is that the voltage across R2 or the voltage across R3? It's actually the voltage across both of them. Oop. Come on. 2.323 volts and 323 volts. All right. So now we've done what I said we needed to do. We have figured out at least one entry in each of the rows going across here. So that means it's just going to be piv and veer to figure out what the other ones are. So if you're trying to figure out the voltage, well, it's veer, V equals IR. So we know all the resistances. I'm trying to write this a little clearer. We know all the resistances. That looks like a T. If you try to figure out the current, well, you can use veer to get, come on, I equals V over R. And to get power, it's just P equals IV. All right, so for R1, what color should we use? We haven't used green yet. All right, for R1 to figure out the voltage. So V of R1 is just going to be that current, I, times R1. So that current is 0.2419 amps. And the resistance of R1 is 8 ohms. So plug that into your calculator, and you'll get a voltage there of 1.935 volts. All right, to figure out the power. Sorry, again, I keep trying to use this like a mouse, and it's not a mouse. The power being used by R1 is going to be I times the voltage of R1. So that power, that I, 0.2419 amps, times that voltage is the voltage we just figured out, 1.935 volts. That's a 9. 35 volts. Plug that into the calculator. And what do you get? You get 0.4683 watts. 0.4683. Sorry, that's a 3, and the units are watts. For R2. Let's go back to one of these blacks. For R2. We already know the voltage there, so to get the current, so the current through R2, I sub R2, is just going to be the voltage across R2 divided by R2. So that voltage is 2.323 volts divided by R2 is 16 ohms. So plug that into the calculator, and you're going to get a current of 0.1452 amps. All right. So we've got a couple choices now to get the current through R3. Actually, I'm sorry, let's go back. Let's figure out the power. Just be consistent. Might as well do it all in a row. The power being used by R2 is just the current through R2, so I sub R2, times the voltage of R2. So that current we just figured out, 0.1452 amps, times that voltage is 2.323 volts. Plug that in and you get 0.3373 watts. 0.3373. All right. That's a pretty color. We haven't done that one yet. Okay, so now we need the current through R3. So here's where we have a couple choices. So the current through R3, you could either think, all right, KCL, well, I know that through R1 and up to this point, I have 0.2, I've got this amount of current, and then it splits, so this much goes through R2, and this much, what's going through R3 has to be this number minus this number, because the current splits right here at this junction. So you can just do it with subtraction if you want. Let's do it that way. If you do that, you end up with 0.0968 amps. And then it's piv again to figure out the power. And the power is 0.2248 watts. Wish I'd made these boxes a little bit bigger. All right. So yeah, it's like Sudoku. There's a lot of ways. Once you have a certain number of clues, there's lots of different ways to get the other clues. So let's see. How can we get the voltage through R4? You could either use Veer again, because you know the resistance of R4 is 32 ohms. That's that number there. And you know that this is the current. So you could just use Veer again. You could also use KVL. So you know that the total amount of voltage around this loop, around the whole thing, actually easier to see if we look at this one, around this thing has to be equal to the voltage of the battery. The total amount has to be zero. But yeah, the voltage drops across these three resistors has to be zero. So you could just take 12 volts and subtract this and subtract one of these. And if you do that, you get 7.741 volts. And then it's piv again to get 1.872 watts. So yeah, there's lots of different ways to do this. Hope you'll forgive me for my sloppy Wacom tablet and penmanship here. I'll get a little better at this as I keep doing it. So hopefully that helps.